To Baozi Training Leetcode solution. If you want the best mock interview experience in North America, feel free to check us out. It's baozitraining.org. We are here to help you land your next dream offer. Okay, today we're going to talk about very classic problem, LRU, least recently used cache. I remember, actually, I got personally asked this question, I think back in 2013 at Google. So it's a very, very classical question. So you should know this problem. If you don't know how to implement LRU, or you're not sure about how hash map kind of things work and W linked list, you should prepare before you actually do interviews. Yeah, LRU, so two very simple APIs: get, given a key, put, given a key and a value, everything is integer, and if the value doesn't exist, return -1, assuming everything is positive. And the challenging part is how do we do everything in O1 time complexity. So once you think about this problem, right, so if you just by using, let's say, a hash map, you can easily say, okay, whenever you get something, right, it will be O1, put something, it will be O1. However, the cache, the LRU works is, if I give you an initial maximal capacity of the cache, if the maximal capacity is reached, that means some item will be replaced from the cache. So I mean, your hash map. So basically, if I draw something, it's like this is your hash map, right? So you have your essentially key and value in this hash map. And then, however, your size, let's say it's only 3. You can only have 3 items in this cache. You can have multiple items in the hash map. That's fine. But the bottom part is the cache size, right? So once you reach the maximal capacity of the cache size, some item needs to be replaced out. So that means this item needs to be basically deleted from the hash map, deleted from here, and then a new item will be inserted. Now the problem is which item needs to be replaced out. And therefore, based on LRU, is least recently used. So whenever the item stays in the cache for the oldest, that it has not been really used, you need to replace that item out. So that pretty much means what is used, right? So whenever you set an item, you put this item in the new hash map, that's considered brand new because you just literally just put it. And then whenever you get this item, get this key, that means it's actually being visited. So it's used. So we need some kind of data structure to store this. A native hash map doesn't have that, because a native hash map, whenever you you set item or get item, the key is not ordered. So the key is not in any particular order. So there's no way you can guarantee that. So the basic idea is basically keeping a doubly linked list. So normally whenever when we say we have list, we normally will have a dummy node, right? For doubly linked list, you will have a dummy node of head, you will have a dummy node of, let's say, tail. Doesn't matter which way you want to insert, but this linked list looks like this, right? You get the idea. So, and then the hash map is more like whenever you insert this item into the cache. So let's say if the cache is empty, so you insert one item. So basically you put a reference, a pointer into this item, and then you put it into, this is also linked because this is a dummy node is also connected. Initially, it will be just 2 dummy nodes, head and tail, connected to each other. So this node will be visited here, right? So you can say, for example, like you want to say, okay, you always insert from the head or the tail, doesn't matter, you just define one way. Let's say you insert it always from the tail. So now the node looks like this initially without this part. So you insert this node, and you insert another node. So the size is less than this, you put another node here. So this is always this latest, right? And then let's say if you get the original node, this one, so what you do is you will disconnect this, and then you put this node back here. Let's say this is 1, right? So because you have this hash map, you know the reference, you can easily get this node. And then because it's a doubly linked list, you can easily detach this node by O1 operation from this doubly linked list. Is basically all the pointers. And then you can, because it's a doubly linked list, you always have the tail. You know how you can add to the tail, right? So because you have the tail, you just also pointers operations, so you can add it there. So essentially that's it. So if you keep adding, putting the items in the list, once you have to put again, so now you need to basically kick one item out. So which one item you need to kick out? So for our particular example, the head, the item, basically the head.next, that item needs to be kicked out because that is the the one item that hasn't been really visited, because as long as you visit it, you will promote it to the tail. So that's basically the basic idea. And so in that data structure, actually in Java is called a linked hash map, and in Python is called a ordered dictionary. So the underlying implementation is literally just what I described, which is a normal hash map and a doubly linked list. So if you decide to, I use Java. So if you decide to use this way, right? So it's you have to extend this linked hash map, because this method is a private, not private, sorry, it's a protected method, which is a package private method, which means you cannot. I really hate like extending things, because if you read effective Java, and it's just, if you use Golang, for example, right? We prefer composition. It's just because it's so clean. So I would rather having this linked LRU linked hash map method contains a linked hash map entity. However, you cannot do that because it's a protected method. You have to override it. So extend and you override. So you can read the Java doc about the linked hash map. So this is the recommended implementation, which is this method. When do you want to remove the eldest entry, right? So you only want to remove it when the size is actually larger than the maximal size. So note here that this maximal size is the cache maximal size, and then this size is basically the hash map's size. And then when you initialize this hash map, note here, this is the initial capacity, right? So this has nothing to do with this maximal size. This could be 100, and this is the load factor, means it's whenever it's reached to 0.75, you need to rehash. And then you want to make it true, because I think false means, I forget, but this is the doc. I think it's access order, right? Order. So this is a recommended way from the Java doc to let you implement, how do you implement a LRU. It usually says, okay, if the size is larger than maximal entry. I think that's Boolean. It should be in the constructors. So let's see, default value, eldest. Access, it's called access order. So the access order is true for access order, which means it's LRU, false for insertion order. So if you put that value to be false, that means pretty much means everything. If the cache size is maximal size is reached, the element that gets inserted, the earliest will be kicked out, because it's based on the insertion order. Okay, so this is the linked hash method, but I would say if you use this in real interviews, it doesn't really tell anything, right? It just means, okay, this linked hash map data structure. So I would rather actually implement the doubly linked list plus a hash map. It's actually pretty easy to do. So you define your node. It's like a doubly linked. I can show it here. It's actually easier. So you can define a node, which is a doubly linked list. You have a previous and the next pointers, the constructor, and then you will have this class called a doubly linked list, right? So this class will have a few methods. Well, of course, you can implement interface, but just for simplicity, I didn't really implement this interface. But you have a few methods. For example, you can get the head of this doubly linked list. You can add the last. So I only implement the ones that I actually need. So normally the implementation order is more like you can start it from here, and then once you started doing this get and set method, you feel like, oh, I need this method, and then you can implement this method here, right? So let's do it that way. So let's say you want to get an item. So you want to check whether this lookup table, which is just a normal hash map, and then you have a doubly linked list class, and then entity. If the lookup table contains this key, that means it has the value. If not, that means doesn't have it, just simply return -1. And then you will get this key. And then you cannot just simply return the value. I mean, you should return the value, but there was one more step. Remember, you have to put this item to the tail of the doubly linked, which means this has already been visited. So I call it promote to last. It's kind of weird because promote normally you want to promote to head and not promote to last, but you get the idea. So what does this promote to last method do? So this promote to last is first I want to remove this item, and then I want to add this item to the last part. And then I would just assume the doubly linked list has a method called remove, and then has a method called add last. Remove, which means remove this node, purely just remove it. And then add last is for this node, right? You have the tail one, and then you add it to the last. And then when you set a method, if it contains the key, so now you still have to do this operation because you want to make sure this item is basically added to the last. You add this item and then you return it. And then if this is basically just if it already contains it, this means you basically set a new value and then you promote it to last. And then if not, it doesn't contain this thing, means it's a new value. And then if the size reach to the maximum capacity, let's say if it doesn't reach to the maximum capacity, you new this node and then you put this node into the hash table and then you add last because this is the last newly added item. And then if it reaches to the capacity, that means you have to delete one method. What do you delete? You need to delete the first item in the head, right? So you get the head, which because we have the dummy node, it's super easy. It's dummy node.next. You get the head and then you remove this from your list. So this list, we have a remove method, which basically I just implemented, remove the code, and then you remove this from the hash table. That's it. So the implementation both ways is basically O1 for get and set, and then the space complexity because you allocated a doubly linked list and also you have a hash map. It's all ON space complexity. So I also attached the official Leetcode solution. If you, the ones which you actually have to pay Leetcode, feel free to download it from there and then see it's pretty much the same thing. All right. As a follow-up, I actually want to talk about it. So there's another cache called the LFU, which is called the least frequent cache. What does it mean is it's not based on the least recently visited. It just means if you have the least of frequency, meaning your visit count is minimal, then you should be kicked out. So one example could be, let's say you have one item, you added one item A, and then you keep getting this item, you get it like a get it 3 times. And then later you add item B and add item C. So let's say this is your cache size. So this, well, you can see whenever you set, does it count for one frequency or not? Let's just say right now the frequency only counts for get, right? So, and then you get B once, you get C once. So this will look like this. A hasn't been touched, note A hasn't been touched for a while, but let's say you want to add item D, which one you need to be kicked out, right? For least LRU, A definitely needs to be kicked out because it hasn't been visited for a while. But for LFU, least frequency, either B or C needs to be kicked out. Now it depends. Let's make it simple. You have to clarify if they're the same frequency, which one needs to be kicked out, right? Could be based on the insertion time. Let's just say it looks like this. So even though B and C are visited more recently, A needs to be kicked out. So this is called the LFU. How do we implement LFU? So actually, I think about it, I don't have a good solution. So if you guys have any smarter ideas, please let me know. So I was thinking I could keep a double linked list plus hash map, right? And then put a heap. So this heap is basically counting the method. So whenever you get, it's still O1 because it's directly returned. But whenever you decide to put, right? So you have to increase the you have to increase the frequency, right? So you have to put a new node into the tree. So that pretty much give it a log n. Let me think. If you get, does it actually a O1? It's actually not O1, right? Because whenever you get one item, you have to increase the value of the item. Now you have to shuffle this heap. So actually get it will be also log n. So essentially this is a log n solution. So if you want to get make sure the get is O1. So I was thinking I could keep a linked list, a hash map, and also array list of doubly linked list. So this key of this array list is a frequency, which means what are the nodes currently are being visited, like in, let's say, once, twice, 3 times. So whenever you add one item, so you get one item, you just directly return. So get will still be O1 because you know which node it is, right? And then you know which frequency it is currently at. So you, based on the frequency, you find that node and you get that node from the W linked list, and then you +1, you insert it into another node. That will be basically get will be O1. So put could potentially be actually ON because you have to list all the frequencies. Because you cannot track, you know, what are the, let's say, the minimal frequency, but once the minimum frequency is kicked out, you have to go through the array again to find the next one. So yeah, I guess maybe just don't use any of this heap. I think the normal implementation could just be literally linked list plus a hash map, and then each node has a counter. As long as you visit the node, you have the counter, and then you will increase that counter by 1. And then if you reach the size, you literally go through all the nodes and find the smallest one, and then you just delete that one. You don't need either a linked list, a heap, or this array list. Let me know if there's actually a better way. So okay, that will be all for today. Thank you very much for watching. Bye.